All right, so the plan for today is we're going to finish up our journey in finding shortest paths, okay? So last time we saw two rather sophisticated algorithms. One was Dijkstra's algorithm, which solves the problem of shortest paths on what types of graphs? Positive weights, right? So we're not assuming that they're directed or undirected. They're just arbitrary directed graphs, but you need to have positive lengths on them. So then we saw another algorithm, Bellman-Ford, that works basically whenever it makes sense. Okay, so on any graph, as long as the question makes sense, which means that the graph has no negative cycles. Okay. That does bring the question of how do you even detect that there is a negative cycle in the graph that we're going to talk about briefly right now. So here's actually there is a rather natural guess of how we're going to detect a negative cycle. Does anybody have a guess? Yeah, you use Bellman-Ford, and how do you?
See if there's any path that doesn't make sense between if you go to the path. I mean, if you go to the edge and then the total cost actually.
So the suggestion was to use Bellman-Ford and kind of to see if things make sense, or maybe if you find any paths that look suspicious. But remember that Bellman-Ford doesn't find all paths, right? So it specifically looks for something. So there's something a bit sharper that we can say about Bellman-Ford. There's a question there? Or? Yeah.
You could run Bellman-Ford anytime if the values keep on changing. Then
right. So here's the intuition. We've proved that Bellman-Ford, after v-1 iterations, has figured out all there is to be figured out about shortest paths, given that there are no negative cycles. Okay? If there are negative cycles, then you can always take them and keep going down and down and down and down. So here's a guess. If you run Bellman-Ford, or rather not Bellman-Ford, one more iteration of updates on all edges, if you see any changes, then there should be a negative cycle somewhere. We're going to prove that now. Okay? Certainly, you don't expect to see any changes if there are no negative cycles, because all the shortest paths have been found. So running one more iteration, or for that matter, any number of additional iterations, is not going to change anything, right? So let's prove that. That's the algorithm. Run Bellman-Ford, and then one additional iteration. So here's kind of what I mean. So you run Bellman-Ford. Okay, so you can update all the edges v-1 times. Now, in addition to that, you tack on an additional iteration. It says for all edges E in the edge set, if update E modifies distance, modifies anything. By anything, I mean, it either changes the value of the estimated distance for either endpoint of the edge, right? Now you're going to say halt and output, some message that says negative cycle. Okay? So that is the proposed algorithm, run Bellman-Ford. And now you have an additional iteration. You don't expect to see any distance to change if there were no negative cycle. If you see something change, then you cry foul. Okay? So this sounds reasonable, but let's prove that it works. So let's say a claim. So this algorithm works. And so one direction is this easier one, and I guess that's what drives this intuition. Which direction is the easier one? So we need to prove that if there are no negative cycles, then we don't say that there are. And if there are negative cycles, then we do say that there are. Right? These are two directions for correctness. Which of these two is easier? The first one, right? So if no negative cycles, then nothing changes. This was the correctness of Bellman-Ford. Okay, so this is fine. But now we need to say that if nothing changes, then there are no negative cycles. So in this one, like again, when something feels intuitive, you need to try to sharpen it down to something that is actually sort of crisp. Okay. Here's an example of statement that looks pretty reasonable, but for all you know, it might not be true, right? So how are we going to say that there are no negative cycles? So here's one way. We say, well, pick a cycle. Let's, for simplicity, let it be made of just two edges. Okay, so let's pick a cycle between I don't know, A and B. Okay, this is somewhere in the graph, right? Of course, if the graph has no cycles, then you're done, right? But so pick a cycle, and for now, let it be with just two edges. Now we want to argue that if these are the lengths, then we want to show that LAB plus LBA is non-negative. That's what it means for a cycle to not be negative. Okay, but we have a hypothesis. It says nothing changes, right? So what does that mean? It means that in the last iteration, when we ran the update, there were specific inequalities that held when I updated this edge and also updated this edge, right? So certainly I do know that the distance, so let's say when I updated this edge, I compared the distance of B versus the distance of A plus LAB, and I didn't do anything because my distance was already better, right? This is when I was updating the edge AB. And when I was updating the edge BA, I compared the distance A against the distance of B plus the edge BA. And I didn't do anything because the distance of A was smaller, right? I click and I'm done. Why? I can add up these two inequalities, I can cancel, and I get this. Right?
But what if we have two vertices, but I only have one directional edge, then I can't write the second inequality, right?
But it's also not a cycle.
Yeah, but it might be part of it.
No, okay, so now we're looking at a small cycle, right? So in general, if you have a cycle that looks more complicated, so just say pick a cycle. So it goes from A to B to C to D. It is a cycle at the end. This is embedded in a bigger graph that you may not understand, but it looks like this, right? So what you're interested in is that the sum of the lengths on all the edges is non-negative. But you can actually write down the very same inequalities for each of those, add them up, and you will get that this entire thing is non-negative. So the proof basically looks the same. Okay? It's just more tedious to write. But this says that this works. Okay? All right, so this is how you detect negative cycles. So the cost of detecting negative cycles is the same as Bellman-Ford, which is V times E. Okay? Now, so what we've seen is that depending upon the type of graph that you have and you want to solve shortest paths, there are different algorithms you should be running, right? So as some sort of kind of summary, right? First, if you have any graph, kind of with cycles or not, and the lengths are positive, then you're going to run Dijkstra. Okay? Anyway, there is a class. Okay, and if you have a graph without negative cycles, then you can run Bellman-Ford, and in fact detect anyways, right? So really you can just run Bellman-Ford. There's actually a class of graphs that for which you can do even better than Dijkstra, okay? Using pretty much what we've learned from Bellman-Ford, and that is the case of DAGs. So if you have a direct acyclic graph, then we can, so I should probably put the times here. So this would be, is quasi-linear, because you have this extra log v due to the priority queue, and this one is kind of either quadratic or cubic, depending upon how dense is your graph. Here, we're gonna, it's basically gonna be a very quick remark. It turns out you can find shortest paths in directed acyclic graphs in linear time. Okay? And to see this, we can come back to what we learned with Bellman-Ford, that Bellman-Ford, when we were reasoning about it, all it taught us, I mean, one thing that we taught, that we learned, is that if you want to speed up finding shortest paths, it suffices to find kind of smart sequences of edge updates, okay? And Dijkstra had this priority queue to help it out, okay? In a directed acyclic graph, notice that all shortest paths are in particular paths, and they follow the direction of the topological order, right? All of them, like, all paths are moving left to right. So this suggests a good order for updating edges. What is it? Topological order, right? And I can just update the edges topological order, and then I'm done. So I don't need a priority queue. I just need to write down the edges in topological order. Okay? How? Well, you just sort the graph. Okay? Topologically sort the graph. And that you can do in linear time. So what you can do here is you topo-sort the graph. And then for all, you can take the vertices in topological order, and then you can look at the outgoing ones for each one of them. So for all VW in E, you update VW, okay? So this is a linear time algorithm. We're updating each edge only once. We're not updating it many, many times. And so that's like linear time. And there's no fancy data structure here to keep track of what to do next, because we know what to do next. We just proceed in topological order. And we've already seen how to use depth of first search to sort the graph topologically. Okay? On directed acyclic graphs, we can also ask the opposite question of shortest paths, longest paths. Yeah, there's a question. Yeah.
Why solve topological software graph with linear time?
Well, we've seen that before. It's you output the vertices in decreasing post number, and producing vertices in post number sequence is just keeping track of the stack as you run DFS. Good question. How would you solve shortest paths? Sorry, longest paths on a DAG? Yeah, so that makes sense. And by the way, why wouldn't we ask longest paths here? Yeah. Yeah, maybe they're positive cycles, right? So you have to keep track of all these things. Anyways, I'm not going to try to tabulate all of this, but notice that kind of in this area of shortest paths, there are all of these interrelated algorithms, and you really should be familiar not just with these in isolation, but in how they're connected and how they portray, like a rather interesting picture of this problem across positive, negative lengths, directed and directed, with cycles or not, right? So directed and directed that's not what I meant. With cycles, without cycles. Okay? All right. So, yeah.
So given that, even in like a directed graph that's not a DAG, if you find the strongly connected components, they're going to give us the DAG. And if I just take the size of the biggest strongly connected components, I can run the outer loop of Bellman-Ford that many times, right? And that should work.
There was a remark about doing like a fine-grained usage of some of these subroutines if you understand the structure of the graph. I'm not going to try to process that online right now, but sure, sounds reasonable. More generally, again, if you have a sense of where cycles are or there aren't, or if you know, in general, this is actually a very good way for us to make exams and problem sets, right? So if there is some structure that tells you, look, you don't have to run Bellman-Ford, there is like some structure that tells you this is a particular way in which you should update the edges and it will save you time because of blah, right? That may very well happen. And I'm not saying that this is all the structure that exists. There's more, just these are kind of distinguished topics. Okay, so now we're actually going to change gears and actually stop talking about graphs for a bit. We're going to touch upon another large class of algorithms. And by today's lecture is in scope for next week's midterm, though today's the last lecture that is in scope for next week's midterm. And that is greedy algorithms, okay? So this will occupy us for, I think, 2 or 3 lectures. And look, at high level, there is no definition of greedy algorithm. It's more of a kind of solution technique, right? Roughly speaking, you have some optimization problem that you're trying to solve. And rather than trying to kind of consider all constraints of the optimization problem, you kind of proceed very myopically. You just take kind of a local best decision, and you just hope you're not going to get stuck with like a bad answer at the end. Okay, so I'm going to immediately give an example of such a thing because it's otherwise it's too abstract. Okay, I do want to say greedy algorithms, sometimes they work very, very well. Sometimes they perform okay. Sometimes they're terrible. It really depends on the structure of the problem. Okay, and sometimes, so greedy algorithms, I view them as rather tricky. You have very reasonable strategies that in some problems are optimal and in others are just like really awful, okay? And a priori, without thinking about it or coming up with counterexamples, it's pretty hard to tell, okay? So I wouldn't say they're like, rather, it's not a very simple class of algorithms to understand. Okay, we're going to go through it as an example to kind of illustrate the idea. And we're going to look at some scheduling problem. So let's define the problem. We have an input. We have a set of intervals. Let's call it A. So the intervals are on, you can think about it on a line. So that's an interval. That's another interval, so on and so forth. We have n of them. These are intervals because xi is less than yi. And these are, let's say, integers. So again, we don't have precision problems. So they're basically, things of this sort. Okay? So that's the input to the problem. So the output to the problem is you want to find a schedule, a set of intervals that are non-overlapping. So non-overlapping means that if you have two intervals in your schedule and you put them on the line, they shouldn't touch one another. Okay? And you can write two inequalities to say that mathematically. Now, so far, if this is all you have to do, you just output the empty set and you're done, right? So these are optimization problems typically. So there's a goal, and you want to maximize the number of things in your set. Okay, so kind of the classical interpretation of this one is, trying to take many courses. So they all some of them conflict with one another, and you kind of have to fill up your schedule with many courses as possible. Okay. All right. So is the problem description clear? All right. So let's write down some sort of algorithm template. And then we can think about how to instantiate it, okay? So a greedy algorithm will start with some sort of empty solution. So you start out by saying, well, I don't know what's going on. I have an empty schedule certainly is a solution, okay? And then you start populating your answer with things that keep it a valid answer, and you try to make it better and better, right? Certainly, an empty answer is valid, but it's just not good. So you're going to say, for instance, while there exists some interval xy that has not been picked and does not overlap with S, meaning that there exists no interval inside S that overlaps with xy, then you're going to choose some next, let's call it x star, y star, among the ones that are not chosen to add to S. Okay? And then eventually you're going to output S. Now, we haven't said how we're going to choose it. That's kind of where the smarts of the algorithm is. But I want to highlight some kind of structural features of this algorithm. This algorithm is greedy because when it puts an interval in the set, that's it. It never comes out. It's not like later it says, I have this other interval here. If I were to put it here and I kick out these other two, right, I would be able to put this other 5 inside, right? It doesn't make this reasoning. It just first make a decision that looks good at that moment, puts it in, and it's committed, okay? Next time it makes, the next best decision, and the next best decision, okay? So it's kind of very myopic, all right? It doesn't kind of change its mind later. And oftentimes, kind of the magic of success or failure of a greedy algorithm is really how do you make the next choice, okay? So, anybody have an idea of what could be a reasonable choice? Yes?
So you sort the intervals by n time, and then you always pick the one with the closest n time so you just don't get.
So the suggestion is you sort by n time and you pick the earliest, earliest not chosen one. So that actually gives the answer that we'll analyze. It actually is. Gives an optimal answer, but there's actually another answer. There's another very reasonable strategy. What is it? It's worth discussing. So here, smallest, shortest. So that's a very reasonable thing to do, right? And by the way, a priori, both of these look equally reasonable. Why should you pick the shortest one or the smallest one? Well, because it leaves the most unused time, right? You have the most space to put other things, right? Why should you pick the earliest one that hasn't been allocated? Well, because it leaves the most time after that, right? So both of these look equally reasonable, yet it's pretty easy to come up with a counterexample of non-optimality for the shortest one, while for the earliest endpoint, we'll see it's actually optimal. So let's see the counterexample for shortest. This is pretty easy to come up. So you have this tiny interval here that maybe you just pick, but really what you should have done is to instead pick these two bigger ones, right? So this is not a good option because the optimal one for this instance is this one, okay? Well, you might say, well, not much worse. Okay, well, today we're talking about optimality, okay? So we're talking about optimality. Is it clear why this is a counterexample? Like, if this is your instance and you want to first pick the shortest unallocated one, you'll pick this one. And then you cannot pick either this or that because they intersect. Now you have a schedule with one class as opposed to two, which is the optimal. Okay? I see some people looking blank. Like, is it clear? Okay. Okay. Fine. So instead, we analyze the earliest end time. So in this case, the earliest end time will first pick this one because that's the first end time. This is the second end time, and this is the third one, right? Once you pick this one is kind of out of the picture because it intersects, and you're going to pick that one. So it will pick 1 and 3, right? I do want to remark that the strategy of picking the earliest end time will just find some optimal solution, but there may be others that will never be picked, okay? So as an example, let me get this right. Let's look at this example, okay? So this greedy strategy will pick this solution, right? Why? Because first it picks this one, then it picks this one. There is another optimal solution. Some other, and it will just never be picked. And that's okay. We don't care, right? There's not a question of equity between the optimal solution. We just need to find any one of them, okay? So just be aware that there may be multiple optimal solutions to the problem, and the greedy strategy will perhaps always zoom in on certain optimal solutions that have some structure, okay? And that's okay. All right, so, but we haven't proved anything, okay? And the way that you prove that a greedy algorithm works is actually rather sophisticated, or at least is requires some thought. It's something that often goes under the moniker of exchange argument, okay? So I want to give, as an example, how you prove that if you run this algorithm with the earliest end time greedy strategy, you in fact do get an optimal solution. Okay? You have to prove that. Okay? All right. So let's give it some space. So we're going to prove the claim that earliest end time as a strategy is optimal for scheduling. So we're going to start first with a proof that's not entirely formal, but it kind of gives the intuition that we're going to really do it properly by contradiction. So I'm going to put kind of proof first in quotes. So here's one way to think about it. So let G be the sequence of intervals that were chosen by the greedy solution. Okay? So I don't know, J1, J2, blah, 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 right? So some number are picked, be the greedy solution. Now we're also going to say let S, S2, maybe they're different lengths, be any optimal solution. Okay? So this is what the algorithm spits out. This is something that just exists. So we can totally talk about it. Right? We would like to somehow compare these. If I'm able to say that, look, this one is no worse than that one, in terms of size, number of scheduled things, then I'm good. Right? Because this is optimal, and this is what my algorithm outputs. So my algorithm then it is optimal. Right? So, okay, well, let's compare them. So either they are the same or they're not. Right? So if G equals S, then we have nothing to prove. So let's assume that they differ somewhere. Okay? So let I be the first place where they differ. Okay? So just start from here and you say, okay, is G1 equals to S1? If yes, then continue. Okay? We have assumed that they're distinct, so somewhere you will find a difference. Yeah? What? The question is, are G and S sorted? I am using an order. I am picking G to be the order in which they're chosen by the algorithm. Okay? And for S, you can just sort it yourself. It is a solution. Okay? And you can sort it by end time. That you can do. Yeah. And that's okay because it's, we didn't assume any structure. Just once it's there, you just can sort it yourself. Okay? All right. So now you can, but the second part about sorting is not necessary, but it helps to think about it like that. So either G1 equals S1 or not. Okay? Let's say, for simplicity, that G1 does equal S1, but G2 doesn't equal S2. Okay? So let's produce a new solution. Consider S prime, okay, that equals G1, which is the same thing as S1, so really is the same thing. You can just put them like that. And now, instead of putting G2, I'm going to put S2. Okay? And then I continue with, do we want to put this one or? No, I'm going to put G. Sorry. G2, and I continue with S3, S4, and whatever comes after. Okay? Let's think. Is this a valid solution? Let's first think. Does G1 overlap with the first entry? No, right? Because the first entry, even if there had been many entries, right? Imagine if it hadn't been already at G2 where they differ. Whatever entries that are before, G2 must be happy with them because they were already part of a solution where G2 came from. Right? So really, the only thing that we should be worried about is, does G2, can it coexist with these? Okay? Well, let's think. When was G2 chosen? At the time that G2 was chosen, all of these were options that had not been chosen yet. Right? They were there. They were here in the set A minus S when G2 was chosen. But look, G2 was chosen to be the one with the earliest end time. So if S2 could coexist with S3 and S4, and G2 was chosen, and S2, by the way, was also among the ones from within G2 was chosen, G2 can only be a better option. Okay? Because it is the one among S2, S3, S4, and blah, 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 and possibly G2, and also G2 because it is different, with the earliest endpoint. So it must be able to coexist with S3 and S4, right? So this is valid. and it has the same size as S, right? So it must also be optimal. Okay, yeah. The question is, what is G2 overlaps with 3? We're just arguing that it cannot. Why? When G2 was chosen by the greedy algorithm, among the unallocated or intervals were not chosen yet, who was there? Well, whatever is not to the left. So S2, S3, S4, and so on and so forth. Now we know that S2 ends before S3 starts. And G2 was the one with the earliest endpoint among S2, G2, S3, S4. So it really cannot do worse than S2 did. Okay? So what we've done is we started with G. It was a greedy solution. Okay? And S. And now we made them one step closer. Okay? So they started out different. And I don't know whether this one is optimal or this one is not, but they had some difference. Okay? And now I made them one closer, and I didn't change the value of S prime. I mean, how big it is. Okay? So it's still optimal. So now I have a new optimal solution that looks more like G. And I can continue in this way until they equal. All right? So this continue in this way, I put it in quotes because it's not entirely formal. To really see this, you have to do it with a proof by contradiction, which is, so I'm going to now flip the proof and do it by proof by contradiction. That's going to be sharp. But it is giving you the intuition for why, things work. It just continuing this way is it's hard to formalize in the positive direction. Okay? But you see what's happening, right? We have this so-called exchange argument. We had an optimal solution. We made it more like our greedy solution. Okay? And if we continue in this way, we keep just going down a path of optimal solutions, and eventually we hit our greedy solution without ever losing optimality. Therefore, our greedy solution must be optimal. Okay? So now I'm going to close the sort of pseudo-proof, because here it finishes and continue this way. I'm going to redo it formally with a proof by contradiction. And this is actually shorter and much easier to understand. So suppose G is not optimal. Okay? If it is, we're done, right? So suppose it's not. Then pick S to be any optimal solution that, however, is closest to G. What does closest to mean? It minimizes their intersection. Both of these are sets of intervals. Among all the optimal solutions, all of them will have some well-defined intersection with S. Pick any of the optimal ones that has smallest intersection with G. Okay? What? Oops. Sorry. The largest intersection. Yeah. Actually, in my notes it says max, so I don't know why I wrote mean. So let's do the prior argument. Prior argument meaning this one over here. Why? Because first, G is not optimal. Therefore, the intersection here is not everything, right? So they must differ somewhere. So do the prior argument. So we know that S not equal to G because S is optimal and G is not. Okay? So we can modify S to S prime so that two things hold. One is S prime is also optimal. And second, the intersection of S prime and G has gone up. It's actually greater than S intersect G. Wait, but that's a contradiction because we picked S to maximize S intersect G among all optimal solutions. Okay? So that cannot be. Yeah?
So if you want to do the prior argument, there is a case where S and G are not equal and you can't do that, and that is if G is a subset of S. Because there's no first place that I can pick that being a set.
So you can still do the prior argument because they differ at that point, and you can move it over, right?
There's no G that is put there, right? If let's say G goes to G1.
Yeah, no, yes, sure. You need a separate part of the branch for the proof, but that's kind of an easy case, and I want to try to argue it right now, though. But yeah, good point. Yes.
How do you know you can modify it to have a bigger?
We just argued it up there, right? We just swapped out an element of S for an element of G to make them more like each other. When you make them more like each other, it means that there is one extra thing in their intersection. Okay? So that was what we did before. You have the two sequences, right? And when you make one more like the other, then the intersection grows. Okay? And the fact that you can do it is due to the greedy strategy. Because you picked the earliest end time, it is precisely what lets you do this exchange argument. By the way, when you're proving that your greedy algorithm works, the particular greedy strategy that you picked should come back in the proof. Yeah. Right, there is another greedy algorithm. So there is this case about the different length that I don't want to get into right now. It's because I want to cover another greedy algorithm that is kind of important for next week. So let me do that also. I'll give you another example of greedy strategy. Yeah.
Okay, so I understand when we modify S and S prime, why the intersection is bigger because it's saying that S becomes more like G, so the area is bigger.
Yep.
I don't see how that supports the first claim that S prime is also optimal because that seems like the part we're trying to prove.
Well, S was optimal. We assume that S is optimal. What does optimal mean? Its size is the largest it could be as a scheduling. If I remove one class and add another class, its size hasn't changed. So it must still be optimal. Okay, so if the optimal number of classes is 80, and I substitute the 80th class for some other class, I still have an optimal scheduling. We don't care about a particular class, we just care how many classes are scheduled.
So this is only counting the cardinality of the set.
Yeah. So this is where you go. Here. We have these intervals. Some of them are big intervals, some are small intervals, some of them are earlier, some of them are later. All we care about is maximizing the number of things that are scheduled, however they look. Okay, that's important because otherwise, indeed, maybe I take out a class from S and I put in a class from G. It does look different, but I'm counting the size. It is the same size. It's just as optimal as it was before. Okay. All right. So here's another. Problem. You're going to see it probably many times in this class. It's called set cover. Okay, it's a combinatorial problem about graphs. So your input, no, not about graphs, about just subsets. Your input, you have some universe U of points, okay? And you have a collection of subsets, S1 through Sm. Okay, so these are subsets of your universe. as an output, you want a subset of indices such that if you take the union of sets over these indices, you get the universe. Okay? And your goal is you want to minimize the size of J, right? So again, there is a kind of, well, also the collection has the restriction that if you take the union over all of them, then you can cover the set. Otherwise, there's nothing to do. So you always have the option of just saying, well, pick all the subsets, and you can cover the universe. And that's kind of the valid output that is uninteresting. And what you do is you want to find the smallest number of sets that cover the universe. And again, here, it is similar to the scheduling in that we don't care how they look like. Some sets may be big, some sets may be small. Doesn't matter, we just pick the smallest one. For instance, if there was one set here that covers the entire universe, that's an okay output. You just output that one, and you have an index set that is a singleton. Okay? So, pictorially, let's say that we have 4 points, and then we have three sets. Okay, so now we have the universe of 4 points, and we have these 3 sets. This is one, that's another one still. So what's an example of a cover? S2 and S1, right? So that's a size 2, right? By the way, I can pick all of them still, right? That would be a cover of size 3. Notice that here, it's not the case that every 2 sets are a cover. So for example, I could pick S2 and S3. That's 2 sets that only cover 3 out of the 4 points. Okay? But here in this case, there's no cover of one set. There are 2 covers of 2 sets, right? There is S1, S2, and there is like S3, S1, right? So that's the kind of problem that you're being asked to solve here. All right, so here is an algorithm that is definitely greedy. It may or may not work. So the natural strategy is that you start out, for now, we're going to start out with the empty set. This is not a valid answer, by the way, if you just output the empty set. Okay? We're just going to start like that. And while we are not done, so namely while if we take all of the things that we have so far, and it's not the universe, then we need to pick some index that we haven't picked yet. And now we have to make a choice in our greedy strategy. So with some property, so we're going to think about it in a moment. We're going to add I to j, and then we're going to output j. Okay? So what is a natural greedy strategy in this case?
Maximize the number of things that we haven't covered yet.
Yeah, so you're going to pick an I with the largest what? So this is the size of the set difference between Si and what I'm going to call Sj, right? So this is the union of j in j, Sj, okay? So you just look at the things you haven't covered. Sorry, what am I doing? U. No, that's fine. No, yeah, that's fine. So I look at all the sets I could pick, right? Now every set that comes, it will, it may have overlap with things I've chosen already, right? But I'm greedy, right? I want to finish fast. I want to pick the smallest number of subsets, okay? So I might as well pick subsets that have the largest number of uncovered vertices, or again, points. I don't know, I keep saying vertices. Uncovered points, okay? This clearly always results into some solution, because in the worst case, I will end up choosing all the subsets, and I know all the subsets do cover, cumulatively all the vertices, points. So this is a greedy strategy. Now, the first thing to note, is that this strategy is actually not optimal. So the largest uncovered, let's call it, strategy is not optimal. So usually the way you convince yourself of that is just come up with some small counterexample. So here it is going to be counterexample. Okay. Whew. Okay, so let's try to reason through this. So what is the optimal solution here? 2, right? So I pick this one and that one, right? Okay. But we have an algorithm, right? So the algorithm doesn't have eyes to look at this one. It just follows the instructions, right? So I claim it will first pick this one, okay, because it maximizes the number of things. I'm trying to get started here, and I wonder if there's like a well-defined start to this algorithm. So if S is the empty set, it maximizes. No, it will pick this one, sorry. It will start with this one. Because this guy is pretty big. There is 1, 2, 3, 4, 5, so that's 10, right? So that's 10 vertices here. And neither of these things is as good, right? There is 1, 2, 3, 4, 5, 6, 7, 8, right? So this doesn't make sense, this doesn't make sense, okay? So it's going to pick this one. After it picks this one, it's wondering, well, I wonder what should I pick next. So neither of these long ones makes sense because it has 3 uncovered, right? It will pick this one, which has 4, right? And then again, neither of these things makes sense is because it would only gain you 1, whereas this one gain you 2, okay? So the greedy strategy here will give you a cover of 3 instead of 2, okay? Okay, but does it mean that everything is lost? Not necessarily, right? So sometimes greedy algorithms are optimal. Sometimes they give you, solution is not terrible. It's okay. Okay, and this is something we'll talk about a bit more formally later in the course. This is a notion of an approximation algorithm. What we're going to do right now is going to prove that this greedy strategy always returns an answer that is not terrible. Okay, that it is within the provable bounds away from optimal. Okay? All right. All right, so here's what we're going to prove. We're going to prove that, let's call it J. This is the one output by the algorithm, so it is the greedy output, is not too big, right? Because we want to minimize it. And we're going to measure it against the optimal, right? Because who knows what the optimal is? We're going to measure it in relation to the optimal. So we're going to write J star. That is the optimal answer. And then, it's going to be not much more than that. It's going to be actually some funny expression that we're going to see in a moment why it comes up. It's basically going to be log n away from it. Okay? So the way to picture this is that there is optimum, right? We cannot get below it because it is optimum. So here we cannot get. And the algorithm is trying very hard to get as close as possible to J star. And it returns something J. And we're saying that this is pretty good because it is always below J star times log n. Okay? So that's why we want to upper bound the quantity cardinality of J. All right? So the proof is short, but packs a lot. Okay? So let's look at it together. So we're going to basically, again, try to, whenever you're not sure where to start, you have to kind of come back to the greedy strategy. I'm going to try to somehow build an argument around it because that's the only thing the algorithm is doing, is just making choices according to the greedy strategy. So we're going to keep track of a quantity. We're going to call it NT. This is the number of uncovered points after t iterations. Okay, so we're running the algorithm many times, and at time t, we have some number of points that we have yet to cover via various sets. So, for example, what is n0? N, right? Or size of u in this case. I mean, that is n, right? Is the input. The input size is a few other things, but this is size of u. All right, so let's see if we can try to relate nt and nt plus 1, right? So if we can prove that we make reasonable progress from nt to nt plus 1, then it means that at some point it will be done. Well, that bounds t, which is what we want, right? What we want to find is that we want to say that t is not too large. So kind of what you expect to happen is that n0 is greater than n1, greater than n2. And at some point, you're done at, some capital T, right? Capital T is exactly this quantity. That's the number of things we've chosen. Okay? We want to say that T is not too large. One way to say it's not too large is that you want to say, well, I make a lot of progress each time, and because in total I only have size of u things, that is the same as saying that T is not too large. So we want to understand these gaps. We want to say that because we're picking this way, these gaps are large. Okay? So here's a tiny lemma. Let me section it off here. Okay? That is kind of the key of the proof. The rest is kind of computations. And that is that n sub t plus 1 is no more than nt minus nt over size of j star. Okay? So you went down nt over j star. Okay? So it's a constant fraction of nt. So the proof is as follows. So I'm not sure I have enough space for that here. let me go up there. Because this is kind of like the only point of the proof that you should understand. So let me do it properly. Nt plus 1 is at most nt minus nt over j star. Proof. All right, so let's see what's happening. So we have our U. Some things have been covered, but now we have this kind of lonely nt out there. We have to pick some set that has not been chosen yet to cover some of them. We'll cover at least one, but we want to say we cover a whole lot of them. One way to say that is we want to refer back to J star and say, look, in J star, there will be some set that actually covers, so not some set. In J star, all of these are covered. All of them. Okay? But look, J star is not very many sets. So if you have J star many sets to cover nt of them, at least one of those sets should be large enough to cover a 1/jth fraction of these. Okay? That makes sense? So there exists, and actually more than that, so let me just be even more precise. Yeah, no, let's say. There exists one of the sets in J star that covers nt over size of J star of these guys, right? Now I want to claim that this set is among those that I can pick from here. Right? Why is that? If that's the case, then I'm done, right? Because then that's one of the choices that I'm entertaining. Yeah?
If you pick all the possible sets in J star, you should be done. If you're not done, there should be one that you haven't picked.
Yeah, so if I already picked this set, right, I wouldn't be considering those nt, right? So the sets that are already in my kind of done here are already over here, right? So none of these are literally covered, okay? So the sets that I'm considering right now are all, so maybe it's not even among J star, maybe it's fewer of them, because maybe some of them are already picked. So this is really worst case, right? All of the ones that I'm considering here, there's some subset of J star that will definitely cover all of these, some sub-collection of J star that will cover all of these, and at least an nt over that many fraction will be in one set. And that's one set that I pick here. Okay? So my progress step is big enough. Okay? Do you need to say this again? Some people, okay. So I want to argue that the set that I am picking in the iteration after the tth one is a set that will cover at least this many extra points. Yeah? The question is, can I clarify what is J star? J star is any optimal collection, right? So here we have a problem, the set cover problem, and I'm saying let's call J star any optimal answer to this problem. Okay? That's why it appears up there as the smallest answer, and that's why I want to bound size of J by so as small a multiple of J star as possible, right? My answer cannot be better than J star, but certainly I can try to make sure it is as close to it as possible from above. Okay. So here, I want to argue that my next choice from t to t plus 1 is going to involve a set that gives me the covers at least this many. Okay, why? Because I'm picking the largest one that among those that I haven't picked yet. So let me argue that. Say, look, in the solution J star that I know nothing about other than its size of J star, all of these are covered, all of the NT. But there's only so many sets, size of J star. So one of them will cover at least a 1 over J star fraction. Because if all of them cover less than that, they certainly cannot add up to covering NT. Okay, so one of them will be like largish. Moreover, this must be one of the sets that I haven't picked yet. Because if I had picked already, then I wouldn't be talking about things that are covered by NT. Okay? So it means that among the choices that my greedy algorithm will consider, that would be one of them. If it doesn't pick that one, it's because we'll have an even better choice. Okay? So it means that the step of my algorithm will proceed this fast. Okay? Good. So now that we have that lemma, we come back here, and we're basically done. It's just the rest is like, this was the only kind of non-trivial part of the proof. The rest is just computation. So there's just 2 lines of computation to get to that point. So not only do we have this, but now we know it goes down pretty fast. And we can say by the lemma, if we kind of unravel that recursion, we know that nt plus 1 is less than or equal to 1 minus 1 over J star to the t, right? Because I just keep unraveling the recursion. And then I have a times u when I get to the end, right? Because that is my n0. Okay? So this is saying that this is pretty small after t operations, after t iterations. How many iterations do I need to do in order to be done? So how small does nt plus 1 need to be in order for me to know that I'm done? Less than 1, for example? When it's less than 1, it must be 0, right? Because the points, if I have less than 1 point left, then I have 0 points left, right? So really, I should figure out what is the smallest value of t such that this quantity is less than 1. Right? So, but we have this like annoying expression here, like 1 minus J star to the t. We're going to use some loose bound here, okay? Some approximation. You can also write this as e to the minus size of J star, everything to the t. Size of u. Okay, so this quantity, 1 minus x, is at most e minus x. Why? You can even like prove it visually. 1 minus x is this line, right? And e to the minus x is this line over here. They meet exactly here, and that's the only place where they meet. Okay? So that's e to the minus x. This is 1 minus x. So this definitely holds, okay? So for the punchline, I need more space. So therefore, we have that nt plus 1 is at most e to the minus t over J star u. Okay? And now, so for t equals J star log e u, okay? And t plus 1 is less than 1, okay? Maybe t is strictly greater than that, I think. Why? Because if I plug in this t here, The j star cancels. I have log e of u, so, but I have a minus in front, so I get 1 over u times u, that is u. Okay? So basically, when you have t just above, let's just say equal, just literally above this quantity, this is going to be strictly less than 1. Okay? But t was exactly the size of j. Yeah? X is 1 over j star. I'm sorry, this is 1 over. Thank you. This is e to the minus 1 over j star. Thank you. Sorry about that. All right, thanks for catching it. So what was t? T is the size of j, right? So I know that I will be done whenever t is literally above this. Okay? So this tells me that size of j is at most j star log e u. Okay? And what is this? You can just think about it as big O of j star log n. Okay? So this is saying that our approximation is within a multiplicative logarithmic factor. Yeah, it's not a very good factor, but it's something, okay? Is it clear? So again, this proof has some computations. They're rather boring and not very interesting. Really, the whole point here is that this strategy is doing something, right? That's why we can prove something about it. What is it doing? It's ensuring that every time that we pick a set, we make non-trivial progress. Because we make non-trivial progress provably, therefore, we have a small number of iterations. A small number of iterations is exactly a small collection, because in each iteration, we pick up one extra set. Okay? So that is equivalent to proving that the algorithm is doing a good job. Okay? Or at least a mediocre job. I'll just briefly mention that actually this logarithm here is there for deep reasons. The set cover is a central problem in combinatorial optimization, and people study how good of an approximation algorithms you can have for various problems, including set cover. And it turns out there's actually a long line of works that is geared at establishing that this is pretty much the best you can hope for. Okay? In the particular case of set cover, it says that unless strange things happen in sort of P versus NP that we're going to talk about probably after spring break in a few weeks, there are very deep reasons for why this greedy strategy is essentially optimal. Okay? But it's by far not obvious and is well beyond this course to see why. So what we've seen now today is like two greedy algorithms that have very, very different behavior. One of them, maybe not the first thing you're going to think about, but the second one, the earliest end time actually turns out to solve the problem exactly, right? Here there is like pretty much the obvious strategy is far from solving it optimally, and moreover, no other strategy for greedy, in fact, no other polynomial time algorithm, not just greedy, no other polynomial time algorithm can do better than this. Okay? We didn't prove that part. I was just talking about inapproximability. Okay, so here's greedy algorithms. We kind of prove them slightly differently. The proof of the optimality of the first one maybe is more representative of the type of arguments you're going to have to do yourself. And remember this keyword of exchange argument, where you start from some greedy solution and some optimal solution, and there is some way to kind of connect them to argue that they're both optimal. Okay? So don't forget, next Thursday there is a midterm. Okay? There might be review sessions. I don't know when they are. Go to them. Today is in scope. Tuesday is not in scope. Okay?